A child climbs 5 meters to the top of a curved water slide shown in the figure, which is virtually frictionless, and slides from rest down into a pool of water. She leaves the slide horizontally, 2 meters above the surface of the water at the edge of the pool. So first, describe the energy cycle for the process from when the child starts at the bottom until she stops moving in the pool. So at the bottom of the slide, she has no kinetic or potential energy, but as she climbs the ladder, she's increasing her potential energy. And she's doing that because she has muscles in her body and chemical energy that are enabling her to do work to climb up the ladder to increase the potential energy. At the top of the ladder, she starts sliding down the slide, so she is turning that gravitational potential energy into kinetic energy, and that continues even after she leaves the slide until she hits the water, and then the water is exerting a drag force on her to slow her down, so that's increasing the temperature of the water very slightly, generating thermal energy to bring her to a stop. In part B, we're going to calculate the speed with which the child leaves the slide. So for that one, we can do conservation of energy, since the slide is basically frictionless. Now, some people say that what about normal force? Because the normal force is a non-conservative force. But the thing is, the normal force is always perpendicular to the child's motion. So, like, for example, when the child is about halfway down the slide, her normal force is pointing in that direction. And when it's perpendicular to her motion, that means the work done by normal force is zero. So even though there is a non-conservative force in this problem, the work done by that non-conservative force is always zero because it's always perpendicular to the motion. So there is no work done by non-conservative forces. So we're going to set up the conservation of energy equation. E initial is equal to E final. Let's define where those two things are. The E initial is at the top, and the E final is at the bottom of the slide. It's not at the very bottom, like when she hits the water, but it's at the bottom of the slide. So we can say K initial plus U initial equals K final plus U final. Next is determine which of those terms goes to zero. So at the top of the slide, it says she starts from rest. So the initial kinetic energy is zero. She has gravitational energy at the top of the slide, so this term will not be zero. At the bottom of the slide, she is moving, so this term will not be zero. And she still has height above the water, so this term will not be zero. So we can go ahead and plug in the formulas. We already know that with gravitational and kinetic energy, the masses will cancel out. So I'm just going to go ahead and write in the formulas without the masses included. So it's GH initial is equal to 1/2 V squared final plus GH final. And when you rearrange this equation for the VF, you should get the VF of roughly 7.7 meters per second. Notice also that even though it's technically not correct, you could have gotten the same answer through using kinematics if you use the last kinematics equation with VO equals 0, A is equal to 10, or say G, which is 10, the delta Y is equal to 3 meters because she started at 5 and she's ending at 2, and the V final is a question mark. If you went through this, you would still get an answer of 7.7 meters per second, and that just kind of works out somewhat coincidentally, but it's not really accurate because first thing is she doesn't go a distance of 3 meters. She goes a vertical distance of 3 meters, but her total distance is the full length of the slide, and also her acceleration is not equal to gravity the whole time. Maybe it is at the very starting point when she's like technically in a vertical free fall, but is as she goes down, the slide is exerting a normal force on her, so she's not in free fall, so her acceleration is not equal to g. This is why that you should solve this one using energy considerations like we did right here. Another thing you can realize if you want to make this problem slightly easier is that, remember we said how the gravitational energy depends on an arbitrary reference point, which we normally make the ground. Well, what if we actually made the bottom of the slide, right here where this blue line is, what if we made that the arbitrary reference point? Then technically, her gravitational energy at the bottom of the slide would also be 0. So then you would just have this equation, gh initial is equal to 1/2 v final squared. The difference is that the h initial, instead of being the 5 feet that we have right here, would now just be, over the 5 meters, would now just be 3 meters because it's the distance from the bottom of the slide. Alright, part C, calculate the speed with which the child hits the water. So we're going to set up conservation of energy again. E initial is equal to E final. After she leaves the slide, she's in a state of free fall, so there are still no non-conservative forces acting on her. So for this problem, we could just do E initial representing the top of the slide. We could also do E initial representing the bottom of the slide if you want. It doesn't really matter because since they're both the same as each other, either one is fine. And then, but the E final, that would be basically as she's hitting the pool. So we'll say it's the surface of the pool. So if we set up K initial plus U initial equals K final plus U final, the initial kinetic energy at the top of the slide is 0. As she's hitting the surface of the pool, that means her gravitational energy is 0 if we go back to defining this, the surface, the ground, as the 0 potential energy point, and then it just becomes the same equation that we had right up here. The GH initial is equal to 1/2 VF squared final, only in this case the H initial is the full 5 meters from the top of the slide down to where she's hitting the pool. And so if all that was solved correctly, you should get that answer of 10 meters per second. Part D, calculate the distance D that she lands from the edge of the pool. So now we're looking at this horizontal distance right here. And this is where you have to start recognizing which problems can be solved using conservation of energy and which problems cannot. And this is a horizontal distance we're looking for. Conservation of energy only talks about the vertical distance when we're dealing with gravitational energy because it depends on the height. The kinetic energy is only about the velocity, and there's no elastic energy in here with the springs or anything. So this horizontal distance, there's no way to figure this out with conservation of energy. It's kind of like solving for time. There's no time in conservation of energy. There's no horizontal distance in conservation of energy. So the thing we're going to do is recognize that, well, this is just projectile motion, and we know the speed that she left the slide, which we solved for right here. So this is just going to become a projectile motion kinematics question. So let's set up the kinematics that we know. In the vertical direction, we know that her initial velocity was 0 because when she left the slide, she was moving horizontally with no component in the vertical direction. The acceleration of gravity, let's define downward as the positive direction since she has no upward motion. So the acceleration of gravity would be positive 10. The delta y, she went down by 2 meters. So because downward is positive, that's going to be a positive 2 meters. And the thing that connects the horizontal motion with the vertical motion is time. So you always want to solve for time if you're trying to connect to the horizontal direction. So if we do the kinematics equation, the third one, delta y, equals VOT plus 1/2 AT squared, where the initial velocity is 0, and we rearrange this for t, we get 2 delta y over a That's going to be 2 times 2 divided by 10. So 4 divided by 10. So we want to take the square root of 0.4, and I'll just leave it as that for right now. In the next part of the problem, we want to find that horizontal distance. So you remember, horizontally, the velocity does not change in projectile motion. So the only equation you can use with projectile motion horizontally is v equals delta x over t. In this case, the delta x is labeled on the diagram as that horizontal distance d. The t is what we have right here, and the v is the speed that she left the slide, which is that 7.7, because that stays the horizontal velocity during her entire path. So the d is equal to v times t when you rearrange this equation. So it's going to be 7.7 times the square root of 0.4, which should work out to be a horizontal distance of 4.9 meters.